chapter is the stuff that I would say is easier as far as carbonyls go, because what you're looking at is the carbonyl carbon reacting as an electrophile, reacting with some nucleophile, okay, and then facilitated either by an acid or a base. Okay. Everything that we look at is doing the same thing. You're either looking at a hydrogen nucleophile, carbon nucleophile, oxygen nucleophile, or nitrogen nucleophile. That is the whole chapter. Okay? There's nothing else beyond that. Okay? When it comes to the oxygen nucleophile, because oxygen isn't that good of a nucleophile, the reaction kind of stalls out with the addition of one oxygen. So then we have the potential to add a second if we activate our reaction enough. So if we're under acidic conditions, we can get the acetal to form by having two oxygen nucleophiles attack. Okay? And what we looked at previously was just two kind of random oxygens as nucleophiles. We didn't specify how they were related to each other. But one of the more important aspects of acetals is that we can pick a different starting alcohol. Instead of picking two independent alcohols, which we see in the first two examples, we can go through and put those two alcohols connected to each other. That's going to change a little bit of the dynamics of the reaction. Okay? So first and foremost, when you're thinking about your acetal reactions, what we're concerned about is that oxygen still isn't the greatest nucleophile, so we want to activate our reaction a little bit more. So we can look at a better electrophile. So in our first case, we have formaldehyde instead of, in the second case, the acetone. The formaldehyde has those hydrogen side groups next to the carbonyl, which don't stabilize the partial positive or our electrophilic carbon in between, at least not as well as our carbons do. So that becomes much more electrophilic, much more willing to react with the alcohols, and we can form an acetal. We get that product favored pretty quickly. When we go through and jump up to, say, a ketone, now we reduce the ability of that product or the possibility for an acetal to form. Okay? And that's really where the challenge is when we're looking at our acetals, is that these are all at equilibrium, and we're trying to force one direction or another. Because they're all not only equilibrium but reversible reactions. When we go through and look at the ketone, we tend to see the reactant favored, meaning we don't push all the way to the acetal in most cases. Okay? How could we help push that towards the acetal? How could we get the products in that second reaction? So what we can go through and do is take advantage of Le Chatelier's principle. If we want to favor our products, we could add an excess of one of those reagents, usually a huge excess of one of our starting materials. The other option is removing one of our products. Okay, the easiest one to remove would be water. How could we remove water? Could look at a distillation. The problem with the distillation is you're looking at the boiling points, the boiling point of water versus any of the other species. Okay. Water is probably on the higher end, so you'd probably end up distilling across your starting materials. Well, that defeats the purpose of the reaction. You now removed the starting materials and prevented them from reacting. So distillation doesn't typically work in this case, but sometimes you can get it to work. What else could you do to remove the water? We could add a drying agent. Okay, we could put in some kind of drying agent that would just soak up the water and get it out of the reaction. There's a couple options. You can do just straight up drying agent, though that doesn't work as well. The bigger issue with just standard drying agents is they also have an issue with decomposition, and we're adding more chemicals, so we want to limit that. So the other option is adding something known as molecular sieves, which effectively filter water out. So they collect water within the shell of the sieve. Okay? The last thing that we would go through and do is say, okay, what happens if instead of adding two separate alcohols, we make sure the alcohols are attached to the same molecule, also known as what kind of a compound? A diol. Okay, so we're looking at some kind of diol separated by some number of carbons. Okay? Typically, the more carbons we've got, the little bit better off we are within reason. Okay? If we had a diol where the alcohol was geminal, okay, we put the alcohols on the exact same carbon, would we expect to get much of our acetal? Okay, why not? What would our result be? So if we go through, and we said there was only one carbon there, if we look at it in blue, this would be our acetal product. What's the problem with that product in blue?
Your four-membered ring.
Four-membered ring. We get massive angle strain. So using the gem dial doesn't really make sense. If we now separate those alcohols out by an extra carbon, as what's shown in this case, what kind of ring do we get? Five-membered. Is five-membered more stable than four? Yeah. Okay. So that could suggest that we get a more stable product. We would expect to get at least more product than if we had done the gem dial. What if we added an extra carbon? Okay, we'll get rid of that. Our product then would have how many members in the ring?
6.
6, which we might predict to be even more stable. What happens if we add another carbon? What happens to the stability of rings when you go beyond 6?
Starts decreasing.
It starts to decrease. So really we hit this sweet spot with 6 or 5-membered rings, which means when we're looking at our dials in an individual reaction, we're really only looking at 2 possibilities. Either the one shown, which is named what? Pretty close. I'd call it ethane diol. Okay. Or we could add an extra carbon and we've got propane diol. Okay. Those are going to be your 2 primary sources for this. We aren't going to go much above that because then we stop favoring that ring structure. Why does the ring structure help us out?
Stabilizes the product.
Okay, so our product energy could go down because we have a stable ring, but it does another thing that's helpful for us. In our intermediate, okay, we have to have that extra red oxygen, our other nucleophile, attack, which I'll go ahead and highlight in purple here. Okay, in our first 2 cases, that oxygen is coming from a separate molecule, which is now floating somewhere in solution. If we have a diol, where is that extra oxygen? It's already attached to the structure. It is very, very, very close. We don't have to wait for this diffusion for 2 alcohols to come in and react. Once we get the first alcohol on, the second one is right there and immediately ready to do that reaction. Okay? So if we go through and generate this cyclic acetal product, we would expect a higher yield of the acetal than if we used 2 independent alcohols. All right? And that's because we do form that nice stable ring intermediate, and once we put one oxygen on, kind of that easiest step, the other oxygen is now close enough that it can do that second nucleophilic attack to get us to that acetal relatively quickly. All right? You'll notice that on their slide they've got 3 steps and 4 steps. What are they referring to? The mechanism for each of those. Okay? You are officially responsible for that entire mechanism. It is 7 steps. Most of those 7 steps are protonation deprotonations. So you put a hydrogen on, you take a hydrogen off. Where it's going to become important is when do you put the hydrogen on, when do you take it off. So you have to make sure you nail down the order. While you may be responsible for it, I think it is a relatively boring mechanism. So it's probably not one I would ask on the test. Okay, what you'd be responsible for is, given an acetal, what species made it? Okay, what's the carbonyl? What are the alcohols that made that? Okay? Or, given the carbonyl and the alcohols, what's the acetal product? Okay? What we ended lecture on yesterday was taking a look at an acetal. Okay? And so one of the things you should hopefully remember about our acetals is that they came from a carbonyl compound and 2 alcohols. Alcohols are all single bonds. If we take a look at our acetal product, we get all single bonds. So the alcohols, as far as a piece go, not going to be particularly easy to find because we could look at a variety of different alcohols in that structure. So what we would instead look for is the carbonyl. The carbonyl is a little bit more different because we now have 2 bonds from one carbon to another oxygen. What carbon atom in that acetal structure looks most like a carbonyl?
The carbon attached to the 2 oxygens.
The carbon that has the 2 oxygens attached to it. which means we could then predict that we would break those bonds, and our ketone would then come in there, and our alcohol would stabilize our other oxygens. And sure enough, we go backwards. That's exactly what we started with. Okay, where does that purple oxygen come from that I drew in the middle? If we were going to look at the reverse reaction.
The water.
Water. Water has to be involved in this reaction. So again, if we want to drive our reaction forward, just like with all the other ones, we can remove water. Why is water's presence an issue? Because that starts to push the reverse reaction. We start to go back towards the carbonyl. So what we can do is limit the presence of water as much as possible, and we could favor our carbonyl over the acetal. What happens, if we limit the presence of water, we favor our acetal over our carbonyl. Okay? If we put in a ton of water, what's going to happen? We're going to favor the carbonyl over the acetal. Okay? So it's adding that extra level of complexity with equilibrium and now applying that back to these reactions. Okay? So to me, that's what makes these really, really difficult, is looking at that extra issue with your equilibrium reactions. Okay? Questions about that? Okay, well, why do we care that it's in equilibrium? Okay, there's a big advantage to something being in equilibrium. That means we can go forward and we can go backward, which means we have a reversible reaction with relatively simple chemistry. That can be very important because what we can now do is build a protecting group. Oops, did I move too far? Oh, that's exactly what we're talking about here. We now have a protecting group. Okay, why is that important? Well, if I started with the carbonyl on the left, okay, and let's say we added something else in there. Say we add a double bond in there. I want it to be cyclohexanone. Hexanone. So we're looking at the single bond. My target is to get to this compound. What changed to go from left to right? So structure A to structure B. What changed?
You added hydrogens.
We put hydrogens into the structure. Okay, we reduced the double bond. What reagents can we use to reduce double bonds? Particularly alkenes. H2, palladium, nickel, platinum. Okay, what's the problem with those reagents?
It also reduces your
They
carbonate.
also reduce the carbonyl. So if I wanted to do this step, I've got a problem. As soon as I add the H2 and palladium, what I get at the end is not my carbonyl, but instead I get the alcohol. Okay, so what I have to do is come up with some way to prevent the alcohol from reacting. Or sorry, the carbonyl from reacting with the H2. So what I can do first is go through and make an acetal. So what I can do is generate that cyclic group. Okay, so now what happens? So now if I try to react that species with H2, what happens? Whoops, let's get the double bond in there again.
It just reduces your bond.
Just reduces the double bond. It has no effect on our oxygens. Okay, why does it have no effect up on that oxygen or those carbons? Stability of the ring allows you to form it, but that's not why we don't have to worry about hydrogen reacting with it.
There's no hydrogens on them to react.
Nope.
The oxygen doesn't want to react.
What do we need to react with H2?
Hydrogens.
H2 is hydrogen.
Oh, okay. The double bond.
You need a double bond. Do we have a carbon-oxygen double bond anymore? No, it's not there. H2 can't react with it because there's nothing there for H2 to react with. Okay? So we could now go through and do my reduction with H2. And I would end up, man, this is really messy. We'd end up with this big old structure with now the double bond removed. Now how do I get back to my carbonyl?
Add water.
Now I can add a bunch of water to push the equilibrium. Okay, so what we've done is protected the carbonyl. Okay? This is an important method that you will undoubtedly see on the ACS test. Okay? However, if you were going to push further on into organic chemistry, or even into any kind of research field, these protecting group chemistries are starting to fall out of favor. Why would they fall out of favor? Don't answer, because I already talked to you.
Do they reduce yield?
That's part of it. To get the reaction where I go from the cyclohexene-one to the cyclohexanone, what happened? I had to do 2 extra reactions. Well, as you guys have seen in lab, what happens to your yield every time you have to do something? It gets lower and lower. So while those steps may be relatively easy steps and even high yielding, if we have to multiply the percent yield at each case to look at an overall yield, our end result is a much lower amount of product. Okay? So economically, it makes bad sense. So what would you do to prevent that? You'd go back to your starting material and you'd use a different starting material and try and find a way to avoid using the protecting group, because it could in theory be cheaper. Okay? There's another big reason why it's falling out of favor. Kind of has to do with cost. That's yield involved. Environment. Okay? One of the big things that is becoming super, super popular with pretty much all fields is this green aspect. You want to minimize the amount of chemical usage, because the more chemicals you use, the more waste you generate. Someone has to take care of that waste, or it just gets dumped on some poor wild animal. Okay? So we want to limit that possible usage of chemicals. Well, to do this protection, what did we have to do? We had to put the protecting group on chemicals. We had to take the protecting group off chemicals. We ran a couple extra steps that really all we did was generate waste. That was it. That's not a very green or nice thing to do. We've now toxified our environment as opposed to get through a couple steps quickly without thinking, whereas we could have gone back and redesigned that experiment so that we could have gotten to our product a little bit more efficiently. Okay? So the idea is to think about what the reactions are, how you're using them, and be aware of the kind of limitations to it. It's not just, oh, I know how to do it, that's the way I should do it. It's, is there a better way to do it? Okay? Questions about that? Okay, let's look at a quick example. How could I do this conversion? What has to happen? So we could look at what has to happen first, and then we can double back and say what doesn't happen. So what changed? What does oxidation mean? Adding oxygen bonds. To go from left to right, what did we do? Left to right, we did what? We lost oxygen bonds.
I'm backwards.
Okay, we lost that pi bond, and they were replaced with hydrogens. What reaction did we do? We did a reduction. Okay. I know it can be difficult to see it, and a lot of times I'll look at a problem and look at the reverse reaction too, which is what I'm going to guess you did. Okay. So just be careful and make sure you answer the question asked. We're looking left to right. Left to right, we did a reduction reaction. Okay, so we need to reduce. What reagents do we have to reduce? We just talked about one. H2 with palladium, nickel, all that fun stuff. Okay, what do those react with? Oh, actually, I'm not sure on this one. Any double bond, I think they will react actually with the ester, but I'm not positive on that one. Okay, what other reducing agents do we have? We have LAH, or lithium aluminum hydride. How many steps would that one be? So if I'm going to write out the reagent, we add lithium aluminum hydride, super, super reactive. It acts as a base as well. To get our hydrogen back on our alcohol, we'd have to follow that up with either water or, I think typically it's actually written as H3O+. Okay. What's our other reducing agent? Sodium borohydride. Okay, NaBH4. The H2 and palladium, that's one I'm a little bit nervous on there. I don't know if that will actually react with the ester. I think the ester is stabilized enough that you won't see the reaction with the H2 and palladium. Okay. Between the lithium aluminum hydride and the sodium borohydride, which one should we use to react at that position? Remember, what we're trying to do is convert this group into this group. So this goes back to those chemicals and knowing something about them. Why the lithium and not the sodium borohydride? You are right.
The sodium borohydride only reacts with ketones.
The sodium borohydride reacts with ketones and aldehydes. It will not react with the ester. So to get the ester to be reduced, we have to use the lithium aluminum hydride. Okay? What's the next issue? Lithium aluminum hydride reacts with what? Esters and ketones and aldehydes. What's the other functional group in there? It's a ketone. What happens if we just add lithium aluminum hydride? It reduces both. Okay? So we can't add just lithium aluminum hydride. We have to come up with some way that we can prevent the ketone from reacting. How can we do that? We can turn it into the acetal by putting on a protecting group. Okay, the most common one is, again, the one we've already seen. Okay, so we could put in our protecting group with an acid catalyst. Should I draw this right? Oxygen, that was a very fat carbon in there. With our ester. We can then follow this with our lithium aluminum hydride and our H3O+. Why do we have to specify 2 steps? Why 1 LaH, 2 H3O+?
Those would react with each other if you don't do it.
Yep, we have to be careful that we don't react the lithium aluminum hydride with the H3O+. This gets us to our OH. Now how can we get to our final product?
Add water to take the protecting group off.
Can add water. Typically we want to speed it up a little bit, so we can add water and H+. Okay. Which we could write additionally instead of H2O and H+ as H3O+. Okay. Makes sense with what's happening with our protecting groups? Okay. So ultimately our acetals are really just a way to protect carbonyls.
Can I ask you a question?
Yeah.
Maybe this is obvious to everybody, but how did the second, is it because it was an ester that the diol wouldn't react with that second?
True. Lithium aluminum hydride reacts with what?
No, go back to the diol.
Oh, over here.
Yeah.
Why did
Why did it stop there?
our protecting group not attack the other carbon? Anybody know? So we could go with equivalence, but then why would it attack the ketone, not the ester? What was that? Finish it off. I think you're right.
It's resonance stabilized.
The ester is resonance stabilized with the oxygen, making that carbon on our carbonyl less electrophilic, which means the ketone will react preferentially over the ester, and we could then propagate forwards. What if we wanted to reduce the carbonyl and not the ester? Now, if we try a protecting group, that's not going to work because it's not going to protect the ester. Everybody see what I'm asking? Erase.
Yeah.
So what I'm saying is instead of this product, we wanted this. How do we do that one? Can't just protonate because that's, we take a look at the things that changed. We added 2 hydrogens. We added this guy and this guy. Sodium borohydride. We don't have to worry about a protecting group. The sodium borohydride will react exclusively with the ketone, not the ester. Ta-da! Don't have to do any protecting. Okay. Other questions on that? Okay. Do we need to see this one drawn out? Either answer is fine, but I'm only going to give you 5 seconds. Okay, there's a yes. So we've got our protecting group and our ethane diol. What is that going to react preferentially with? Aldehyde or ester? Reacts with the carbonyl carbon, right? Which carbonyl carbon is more electrophilic? The aldehyde. Why?
Resonance stabilized.
There's resonance stabilization with the ester, preventing the ester from reacting as quickly. So we would expect the aldehyde to react first. And we've got our, our ester. Now what happens? So that gives us our first question. Question mark. What about the second question mark? How do we move to that next product? What happened? Yep, we did a reduction. All right. We ended up adding hydrogens to our structure. We're going to add a hydrogen to this carbon. We're going to add a hydrogen to our oxygens as well. What reagent do we use to do that reduction? We'll use our lithium aluminum hydride. They're still attached. That looks like LAA. Our lithium aluminum hydride is step 1, and step 2 we can do our H3O plus to go ahead and protonate. Okay. What is the H3O plus going to do for us? Yes, it's going to protonate our alcohol, but at the same time, what does our H3O plus do? Yes, it acts as an acid. It's going to hydrolyze off our acetal. Okay? So we can add our lithium aluminum hydride and our H3O plus, and then immediately we hydrolyze off our aldehyde, or hydrolyze off our ester at the same time, or back to our aldehyde. How do we get the next one? What changed there? There's a big hint. Go through and slightly redraw this. What happened? Our nucleophilic oxygens attacked our electrophilic carbon. To do that, how do we facilitate that acetal formation?
Remove water?
Yeah, how do we remove the water? So we'd add H+, and then we could also say at the end we could remove H2O, because that's going to be our other product in this case. Okay. Get the idea on how you should be processing these? So we could jump beginning to end, break it down into smaller steps, evaluate each of those steps. Okay? Questions about that? Okay. Next one is our Baeyer-Villiger reaction. We're again using an oxygen nucleophile. This one's a little bit more interesting because our oxygen nucleophile also happens to be what? What's the name of that functional group? It's a peroxy acid. So that oxygen is still nucleophilic at the very end, so it can do its standard attack, and we end up now with a very, very weak bond. We can shift our hydrogen around. We end up with a very weak bond between our oxygens, which I'm trying to highlight in orange there. That bond naturally wants to break apart, given a little bit of heat. So what happens? We can take the electrons in that bond and move them towards our other oxygen. But then we've got a problem. Our red oxygen has now lost electrons, so it needs to get electrons from somewhere. What ends up happening is we see an alkyl shift. So the Baeyer-Villiger reaction, we could actually add a step further to that. It's not just the Baeyer-Villiger reaction, it's a Baeyer-Villiger rearrangement. The end result is that we start with a ketone and we end with what functional group? We end with an ester. The exact mechanism, while it's interesting, I probably don't care too much about, and I don't think you'll ever see it again. But you should be aware of it because you will see it for sure, at least on the next test, at least one question. So what's happening with our Baeyer-Villiger rearrangement is that we're adding a peroxy acid. That peroxy acid acts as a nucleophile, again with our carbonyl compound, forces a rearrangement so that we end up with potentially an ester or even a carboxylic acid if we started with an aldehyde. Not starting with an aldehyde. Actually, yes. Which step in the equilibrium is the most likely the slowest? That's an interesting question. What do you think? The proton transfer, I would argue, is going to be really, really fast. So we've got step 1, 2, and 3. Step 2, you're looking at a hydrogen being transferred from one part of the molecule to another. You'll notice that the arrows show what type of transfer. Intra or intermolecular? Intra. Didn't we say intra were really, really bad? Shouldn't do those. Why is it okay to show an intramolecular hydrogen transfer? How many atoms are in the transition state? 5. Can we get a 5-membered ring? Yeah. So that transition state is reasonable enough to suggest that we probably do get an intramolecular hydrogen transfer. We're not looking at that hydrogen being pulled on and off from the solvent. It's probably happening within the molecule. It's a hydrogen transfer. Any hydrogen transfer in general is fast. So step 2 is probably not the slowest. I would probably argue the first one. We have to get that oxygen to actually attack our electrophile. Not going to be the easiest thing. Our very last step, we already have a very, very weak oxygen-oxygen bond that we now made even weaker by putting on a carbon instead of hydrogen. And carbon's more electronegative than the hydrogen. So we've polarized that bond even further. So to me, your first step is going to be the slowest because of just the dynamics of everything else. Questions about the Baeyer-Villiger? I think there's a pretty big question that comes out of this. What if this is your starting material? What product do we get? So the Baeyer-Villiger did what? Took a ketone and made it an ester. How do we make an ester? We need an oxygen next to carbonyl. Right? There's an ester. Is that the only ester I could have drawn? Nope. Also have this as a possibility. So what does that mean? Which is our answer? Well, how did they figure it out? They went to experiment and tested a bunch of different molecules and saw what those patterns were. Okay? The end result, if I remember this correctly, is we see the top one as our answer. Okay? Remember, the Baeyer-Villiger doesn't show up a whole lot, and so I don't have it memorized, but I did do it right. So our top one is the predicted product. We don't see the bottom one. And we know that because we have memorized the rankings on those shifts. So what we're saying here is hydrogen will shift first, then a tertiary, then secondary, phenyl, primary, and methyl. So the methyl is the least likely to migrate. The other R group is more likely. All right, so what we're looking at shifting is this carbon or this carbon, red or purple. If we take a look at our red, we're looking at what kind of a substitution? It's tertiary, and our purple is primary. Which one preferentially shifts? Our tertiary. So if we went through and looked at our product, what we're looking at forming would be this ester. Okay. So what happened is we shifted, we went from the red bond to now the purple bond. Okay. That was our shift. So we shifted that R group from our carbonyl carbon to the oxygen. Okay. So Baeyer-Villiger, we make esters. That's what you really need to get out of that. Questions? I don't particularly like your face there, and I don't mean it like that, but do you have a question on that? Not a specific question. Okay. I think there's one question on sapling about the Baeyer-Villiger. I would recommend doing a couple problems just to kind of get a feel for it. Ultimately, to me, it's just a memorization one. Okay. I don't see any predictable pattern on why we got the rankings that we did for those individual shifts. That's just what happened. Okay, so you would just kind of have to know those. Okay. Last one the textbook includes is the sulfur as a nucleophile. I've got it classified under oxygen nucleophiles. Why should I classify it there? Sulfur is right underneath oxygen on the periodic table. They're going to react the exact same. Okay? So we can use sulfur or thiol compounds instead of alcohols and do ultimately the same chemistry. Okay? What's going to be the advantage of using the thiol over an alcohol? Which is the better nucleophile? The thiol, because it's more polarizable. Okay, so we get a slightly more nucleophilic nucleophile in our sulfur, so we can actually push product formation a little bit better than we could with the alcohols. Okay? So you end up with similar compounds. We end up with thioacetals, thio for the sulfur, and we're still getting that pseudoacetal formation. Okay? All the chemistry as far as the mechanism goes is the same. So any place that you saw a mechanism with the oxygen, erase the oxygen and put a sulfur, you got the exact same mechanism. Okay? Any other questions on that? Okay, so what we're going to look at now is very quickly moving to nitrogen nucleophiles. We're going to talk about some general things first. To start off with, which is the better nucleophile? Oxygen or nitrogen? Why is nitrogen the better nucleophile? It's less electronegative, so it may have less electrons, but remember, at any given instant, you can only share one pair of electrons. Okay. Nitrogen is more willing to share the electrons it has because it's less electronegative, which means nitrogen is our stronger nucleophile. As far as our carbonyl chemistry goes, nitrogen is such a strong nucleophile that it will react nitrogen and oxygen both have that lone pair, so they're going to act very similarly as far as a reaction goes. So in our very first step, when we switch from an oxygen or an alcohol over to an amine, that very first step will be exactly the same, be it our hemiacetal or hemiimine, so halfway to becoming our fully saturated nitrogen issue. The second step is where we see something different. Once we form the hemiacetal, how did we move to the acetal? We had another alcohol come in and attack. We had to have another alcohol come in and attack because it's not as nucleophilic. Nitrogen, on the other hand, is much more nucleophilic. So what ends up happening after the first attack? We still get a second attack, but that second attack comes from the same nitrogen. Okay? So instead of now swapping between, let me erase, well, I can just erase everything. Instead of starting with, I don't know why I picked this structure, it's awfully big. And if we used an alcohol nucleophile, we end up with our acetal. With our nitrogen, we still go through and put on the nitrogen, but our second attack happens from the same nitrogen, which means we need to form that second bond with the same nitrogen. So what we end up with is doing effectively a substitution. We replace oxygen with the nitrogen. So our nitrogen nucleophile does slightly different chemistry because it's more nucleophilic. We don't need that second oxygen or that second nucleophile to come in. The nitrogen is nucleophilic enough that it will do that attack immediately. Okay? And it will push us all the way to doing effectively a full substitution. And we completely kick out the oxygen from our carbonyl and we replace it with that nitrogen. So it's kind of neat in that respect. With our acetal reactions, we had those acid or base catalyzed. Okay? And that's ultimately because our alcohols could go both directions pretty quickly. Which one's going to be best to work with our nitrogen? What's the issue if we add hydroxide? It's another nucleophile. Hydroxide versus a neutral nitrogen, which is a better nucleophile. The hydroxide. So our base catalyst is going to be a bit of an issue because the base catalyst could act as a secondary nucleophile. So we aren't a big fan of base catalyzed nitrogen reactions. We're going to tend to see those being under acidic conditions. All right. What will a product most likely look like? We just addressed that. We're looking at the nitrogen being doubly nucleophilic, and we end up seeing the complete swap out for our nitrogen versus our oxygen. There are some caveats to that. To do that, our nitrogen has to lose two bonds that it started with. Those two bonds would need to be two hydrogens. So to get this complete structure, the complete swap out that we've got here, we had to start with a primary amine. What if we had a tertiary amine? Once it attacks, we don't have that nucleophilic character anymore. We can't regain the electrons. So a tertiary amine isn't going to do the same chemistry. It doesn't have that secondary nucleophilic ability. How about a secondary amine? Secondary amines have the potential, but again, their chemistry is going to change a little bit, and we will look at those in just a little bit. Okay? But first, what we're going to do is a quiz. And since I really didn't want to write all this stuff down, acting as our nucleophile. Ultimately, the same general mechanism. We've got the acid reacting with our carbonyl. Remember, we said the base conditions were going to be a bit challenging with our basic nitrogen. So what we're going to go ahead and do is protonate our carbonyl to activate it, to make the electrophile more electrophilic. The nitrogen lone pair can now be shared. We end up breaking apart our structure, or breaking apart that pi system, so that's where we're moving through here. What type of reaction happened in that second step? What's that? It's a nucleophilic attack, or we could look at it as the second step of an addition reaction. What was our first step? Acid-base, or our addition first step. Okay. Next step of the reaction, what happens? Have we generated a stable species? No. Why is it not stable?
You have a formal charge?
We have that positive formal charge. So we need to fix that. How do we fix that? Nitrogen is going to take electrons away from the hydrogen. Okay, so we end up losing a hydrogen. You'll notice that what they used was A to remove the hydrogen. They didn't specify what that atom was. Any ideas what's going to be the most basic atom in that solution? Probably the nitrogen, actually. So we'll have excess amine. That amine is probably going to be what's pulling off the hydrogen. The conjugate base isn't going to be very basic because it needed to act as what in the first step? An acid. If it's going to act as an acid, what does that mean about the conjugate base? Can't be very basic.
But it's confusing how they put A.
I know. Okay. What happens in the next step? Or sorry, what type of reaction was that? In here? We're looking at just a straight acid base, nothing fancy beyond that. What we now end up forming is effectively the equivalent of our hemiacetal. Okay. It's a little bit different in this case because we have a nitrogen, okay, instead of an oxygen. What happens now? Just like we did with the hemiacetal, we will protonate our original carbonyl oxygen. In what type of a reaction? Acid-base. We could again even approach this as the first step of our addition. It's a little bit weird to look at it as the first step in this case because we don't have a double bond to add to. So that's a little bit odd to phrase it as an addition. It's better termed as our acid-base reaction. Okay. The result of that is we now have a phenomenal leaving group in our water. You will notice that what they decided to do as far as the mechanism was have the water leave at the same time as the nitrogen came in and attacked. Okay. Really going to depend on what the other atoms are around it, okay, what those carbons are. Why would that matter for the mechanism? What type of mechanism did we just show in this case? It's an SN, so it's a nucleophilic substitution, sort of, and we're doing it in one step, so we'd call it SN2. If we had a good leaving group and a stable potential for a carbocation, we'd call that SN1. Okay, so it really depends on that intermediate to derive that. The other thing that makes this a bit odd as far as SN2 or not is that this is all done intramolecularly, within the molecule. When we look at an SN2 reaction, what happens? We're looking at two molecules coming together. Is there a better name we could use instead of an SN, where we have a nucleophile attack but generate a double bond? We could have our E2 as shown because it's again one step, but it could also be classified as E1 if we formed that carbocation. Okay? The end result is that we form our nitrogen-carbon double bond. Is that nitrogen stable? Too many bonds and positive charge. How do we fix that? Nitrogen can take electrons away from the hydrogen, and we end up with our final product, okay, the equivalent, or the nitrogen equivalent to the acetal, where we've completely substituted out our oxygen for the nitrogen. This is now a new functional group. These are referred to as imines. Okay, a nitrogen that is connected to 2 carbons, and we've got that nitrogen carbon double bond. Okay? While I do not expect you to know that that is called an imine, be aware that that might pop up both in the homework and on your ACS test. Okay? So you kind of got to be a little bit cautious with that name. Questions about that mechanism? I know we just did that really fast. The imine in this case, so now I got to think back to the definition of an imine. I think the imine is just a nitrogen carbon double bond. So that R group I think can be a hydrogen as well. It's effectively the same as a ketone. Yep. Which is ultimately what we were saying happened. We completely substituted out the oxygen and put in a nitrogen. Okay. This mechanism only works if we have a primary amine. Why? We need to replace the carbon-oxygen double bond with a nitrogen-carbon double bond. So we have to be able to remove 2 bonds relatively easily from the nitrogen. What are the easiest bonds to make and break? It's a hydrogen. Okay? So we need to have a primary amine to be able to go through and make the imine.
It says with the nitrogen attached to hydrogen or organic group.
Or organic group? Cool. It's nice when I sometimes remember things. Okay? Other questions about what's shown up there? Okay. All this is really saying is that we have a pH dependence with this. If we make it too acidic, what happens? What's the issue with our primary amines? In fact, any amine. They have electrons. Those electrons are good at making it a nucleophile, but they also make it a base. If we make our solution too acidic, what happens? The amine acts as a base and picks up a hydrogen. What charge does the nitrogen become? Do we have a nucleophile? Nope, reaction can't occur. Okay? If we go through and try and make it too basic, what's the problem? So how do we make a solution basics? We have to add something like hydroxide. What's the issue with hydroxide? Okay, it could deprotonate the nitrogen, but then that just makes the nitrogen even more nucleophilic.
Dihydroxide can actually nucleophile.
Our hydroxide could act as a nucleophile as well. Okay, so with our amine nucleophiles, we have to be a little bit careful with our pH, because if we go too acidic, we lose the nucleophile. If we go too basic, we end up doing competing reactions. Okay? We also don't have the ability to activate our carbonyl. Okay? Primary amines versus our secondary amines. So if we take a look at the primary amine, that very last step, okay, we went across and formed the imine by losing that hydrogen. If we go through and take a look at a very similar mechanism, but instead we do it with a secondary amine, we'd get all the way up to that last step. Okay, so what we're trying to compare here is the very last step of those reactions, both primary and secondary amines. So if we go back to this, take a look right here at that last, that very last step. I'm sure those sound effects are awesome when watching videos. Our very last step of that reaction, okay, if we used a secondary amine, what do we have for that hydrogen? We would have an R group, another carbon. Okay? Problem with that is then we can't remove it using our base. So we can't go to forming the imine. So what happens instead? Well, the end result is that nitrogen still wants its electrons. Says, this sucks, give me my electrons. So instead what it does is it goes to the nearby pi bond. The pi bond with higher energy, it pulls the electrons away from that pi bond. But then what happens to the carbon? It becomes positively charged, and it gets pissed and wants electrons. So we end up still doing an acid-base reaction, but that acid-base reaction happens 1 carbon further away, and we end up forming the double bond between 2 carbons. Okay? Pseudo-drastically changes our end result. Instead of having an imine, we now have an enamine. What does enamine, particularly when we phrase it in that sense, sound like? We have an ene, as in an alkene, and we have an amine, as in our nitrogen with all single bonds out to carbons. Okay? Mechanistically, it is the same except for that very last step. Okay? One of the things that's going to make this interesting, or where this structure, our enamine, is going to pop up again, is in the next chapter we look at, chapter 22. Because what we're going to start to evaluate is the acidity of the carbon attached to our pi bond, okay, or next to our pi bond. And it turns out that that carbon now becomes actually quite acidic. Okay? Definitely didn't get to cover everything I wanted to do today. I will consider recording another lecture and posting it over the weekend for you to go through and watch, so that on Monday we can do a little bit more problems with practicing with all of the reactions within this chapter. Because ultimately I think that's going to be better for you guys, is to do the practice. Okay? So yeah, we've got the Wolff-Kitchener reduction, which I believe is the end for our reactions. We'll go through with the rest of nitrogen, which is the reduction. And then it's spectroscopy. There's really only a couple things to pick up with spectroscopy. And then we've got nomenclature. The synthesis section is ultimately just talking about how we run reactions. So that's where I would do different problems. Okay? So I will probably, is that the only thing left, is the synthesis and that? So I will probably post an additional lecture talking about the Wolff-Kitchener reduction. You should be able to go through and do most of that chemistry on your own. That very first step, you should be able to do. Why? It's the formation of, all intents and purposes, an amine, okay, which we just saw the mechanism for. Okay? Yeah, we'll go ahead and finish that up next week.